Have you ever, like, really stopped to think about a compass?
Yeah.
You know, that simple needle, always pointing north. Feels ancient, right? So straightforward.
Yeah, total familiar.
But the physics, underneath that, the actual magnetism, that's where things get, well, pretty wild.
Oh, absolutely.
It turns out magnetism, as we understand it now, is fundamentally a quantum thing. Much stranger and, honestly, way more fascinating than you might think.
It really is. That everyday gadget is just, scratching the surface of this incredibly deep quantum reality.
And that's exactly what we're diving into today. Welcome to this deep dive on quantum magnetism, spin waves, and light.
And this isn't just us riffing. We're basing this discussion on some really insightful notes that you, our listener, sent over.
That's right, compiled by Sylvia Viola Kosminski from the Max Planck Institute for the Science of Light. And these were originally for masters or advanced bachelor students, so it's pretty advanced stuff.
Yeah, it definitely assumes you've got a good handle on quantum mechanics, EM, solid-state physics. But our goal here, our mission for this deep dive, is to pull out the really key ideas, the important insights.
Kind of give you a shortcut, right?
Exactly, a shortcut to getting up to speed on a field that's really at the cutting edge. We'll dig into some surprising facts, keep it engaging.
Okay, let's get into it. Compasses. They've been around for ages. How can something like magnetism, which feels so everyday, be fundamentally quantum? What did the old physics miss?
Yeah, good question. Classically, the understanding was, well, magnetism comes from moving electric charges. Ørsted, back in 1819, he showed a current could move a compass needle.
Right.
And Ampere then suggested, okay, maybe all magnetic fields come from moving charges. You could even picture like an electron orbiting an atom, a tiny current loop,
Okay.
generating a magnetic moment tied to its orbital angular momentum. And just as a side note, we still haven't found those magnetic charges, those monopoles just floating around freely, though they can sort of pop up as effective things inside certain materials.
So that classical picture, electron, circling like a little planet, creating a magnetic field, it makes a kind of intuitive sense. But I guess that picture breaks down.
It does, big time. I mean, first, those stable orbits. Classically, they just shouldn't exist. The electron would radiate energy and spiral into the nucleus. You need quantum mechanics just to have stable atoms.
Ah, right.
And then comes the really, really weird part. The electron has this intrinsic angular momentum. It's called spin.
Intrinsic, wait, you mean it's not actually, like, physically spinning like a tiny ball?
Exactly. That's the mind-bending part.
Wow.
It has absolutely no classical analog. It's purely a quantum thing. Physicists figured it out by looking at things like the anomalous Zeeman effect.
Zeeman effect, splitting energy levels in the magnetic field.
Right, but they split in ways you just couldn't explain with only orbital momentum. And understanding how that spin relates to the magnetic moment, that actually requires the Dirac equation, which is, relativistic quantum mechanics. Deep stuff.
So the electron isn't just orbiting, it also has this built-in spin, and you said this spin contributes more to the magnetic moment.
Roughly twice as much for a given amount of angular momentum compared to the orbital part. Which is why the total magnetic moment isn't just proportional to the total angular momentum, it's complicated.
Okay.
And getting this foundation right is just crucial. Without quantum mechanics, without spin, you fundamentally cannot explain why magnets work at the atomic level.
Yep.
It's the secret sauce, really. It scales up to everything we see. Classical physics just doesn't cut it.
Okay, so the secret sauce is electron spin. That's where magnetism starts in one atom. But then you take something like iron, a strong magnet. How do all those tiny atomic moments line up together? It can't just be them acting like tiny bar magnets attracting each other, can it? That feels too simple, maybe.
That's the natural thought, isn't it? The intuitive idea, maybe it's just classical dipole interactions, all those little atomic magnets pulling on each other.
Yeah.
But here's the kicker. That interaction, it's incredibly weak. Far, far too weak to explain why iron is magnetic at room temperature. Dipole forces are only really strong enough below about, say, 1 Kelvin, minus 272 Celsius.
1 Kelvin, seriously. So my fridge magnet, the force holding it on isn't just tiny magnets attracting each other. That's genuinely surprising.
It surprised physicists, too.
Okay, so if it's not basic magnetic attraction, what is strong enough to lock all those spins together? This is where it gets really interesting.
Right. The answer is purely quantum mechanical. It's called the exchange interaction.
Exchange interaction.
And like spin, it has no classical counterpart. It comes from, believe it or not, basic electrostatics. The repulsion between electron charges combined with the Pauli exclusion principle.
Whoa, wait. Electrostatics, like charges repelling, and Pauli. That's the thing about electrons not being in the same state, right? How does that lead to magnetism?
Okay, let's try a simple picture, like a hydrogen molecule, H2. You have two electrons. Now, electrons are identical, they're indistinguishable. And Pauli says they can't be in the exact same state.
Uh-huh.
Because of this, their spatial arrangement where they are likely to be found actually depends on whether their spins are pointing the same way, aligned, or opposite ways, anti-aligned.
So their spin orientation affects where they hang out spatially.
Precisely. If they're aligned, the Pauli principle forces them to be, on average, further apart to satisfy the rules. If they're anti-aligned, they can be closer together.
Okay.
And since electrons repel each other electrostatically, being further apart or closer together means a different amount of electrostatic repulsion energy. It's a huge energy difference compared to the weak magnetic dipole forces.
I think I see. So it's not a direct magnetic force between spins, but the quantum rules force a link between spin alignment and spatial arrangement. And that difference in space causes a big difference in electrical energy.
You got it. It creates an effective interaction between the spins. We describe it with something called the Heisenberg-Hamiltonian, but basically it creates a very strong preference for spins to either align, ferromagnetism, like in iron, or anti-align, anti-ferromagnetism. That's where strong magnetic order comes from.
Wow, okay. That is an aha moment. The power of a magnet isn't really magnetic in origin, it's electrostatic, filtered through quantum rules. That's fundamentally weird and cool. Quantum mechanics just doesn't care about our intuition, does it?
Not one bit. It really shows how deep these quantum effects run, even in everyday things.
Okay, now we understand why spins lock together. But what happens if you disturb that perfect order? Like if you heat a magnet up or just poke it? We know vibrations in a crystal make sound waves, phonons. What about wiggles in the magnetic order?
Great analogy. You're right. Just flipping one single spin completely over in a perfectly ordered magnet takes a lot of energy from that exchange interaction we just talked about.
Too expensive, energetically.
Exactly. So the system finds a cheaper way. It creates collective excitations, ripples in the magnetic order. We call these spin waves. And when you quantize them, like light quanta or photons, the quanta of spin waves are called magnons.
Magnons. Okay, so it's not one spin flipping,
Right.
but a wave, like the crowd doing the wave at a stadium.
That's a perfect way to visualize it. No single person runs across the stadium, but the wave propagates. A magnon is similar. It's a collective procession of spins. Think of it like a deficit of one unit of spin alignment, but that deficit is spread out and moves through the material as a wave.
So each spin just wobbles a little bit in a coordinated pattern.
Exactly, a propagating wobble.
Right.
And importantly, these magnons behave like particles themselves, or bosonic quasi-particles.
Right.
Bosonic means they can pile up in the same state, unlike electrons, which are fermions.
Got it. And these magnon waves, they have properties like energy and momentum.
They certainly do. They have a momentum k and an energy omega of k linked by a dispersion relation, which just describes how the energy changes with momentum. And here's something interesting. For many simple ferromagnets, the energy of low momentum magons goes like momentum squared, K2. That's different from sound waves, phonons, where energy usually goes linearly with momentum, K, at low energy. That K2 dependence is actually a sign of the underlying rotational symmetry of the magnet.
Ah, neat detail.
And yeah, these magnons can also bump into each other, interact, which means they don't live forever. They have a finite lifetime.
So basically, if we want to understand magnets at anything other than absolute zero temperature, or how they lose energy, or maybe even use them for computation,
Yeah,
we need to understand magnons.
absolutely essential. They govern the thermal properties, energy transport, damping, and yeah, they're now being looked at very seriously as potential information carriers for new kinds of devices.
Okay, so we've got these magnetic waves, these magnons, rippling through materials. Now, what happens if we shine light on them? Can light and magnetism actually, talk to each other in a meaningful way? And how do we get them to speak loudly enough?
Well, people have known for a long time that light and magnetism do interact, classically anyway. The most famous example is the Faraday effect.
Right. Polarized light goes through a magnet, and the polarization rotates.
Exactly. That happens because the magnetization slightly changes how the material responds to the light's electric field. It changes the optical properties.
And doesn't work the other way, too? Can light affect the magnet?
Yes, that's called the inverse Faraday effect. The light itself can exert a tiny, tiny effective magnetic field on the spins, a little pushback, but the key word there is Tiny.
How tiny?
Extremely tiny. For a material like YIG, yttrium iron garnet, which is a workhorse in these experiments, the effective field from a single photon is something like 10 to the minus 11 Tesla.
Wow. Okay, compared to the Earth's field, which is like 10 to 6, that's minuscule, basically nothing.
Pretty much negligible for most purposes. The intrinsic coupling is just really, really weak.
So that sounds like a dead end for using light to control magnetism efficiently. How do researchers get around that? How do you amplify that whisper of an interaction?
That's where the breakthrough of cavity optomagnetics comes in. It's a really clever idea.
Okay.
You take your magnetic material, like that YIG sphere, and you put it inside a high-quality optical cavity.
Like a pair of mirrors facing each other.
Sort of, yeah, or other structures that trap light. The point is, the cavity makes the photons bounce back and forth maybe thousands or even millions of times before they escape.
So you're forcing the light to spend much more time inside the magnetic material.
Precisely. Instead of just zipping through once, it interacts over and over and over again. It dramatically enhances the effective interaction time.
Giving them way more chances to talk. It amplifies the conversation.
Exactly. And this amplification can be so strong that you reach what's called the strong coupling regime. The photons, light quanta, and the magnons, spin wave quanta, become hybridized. They form new entities that are part light, part magnon.
That sounds seriously quantum.
It is. People do this with tiny, polished spheres of YIG, for example. Light can circulate around the edge in what are called whispering gallery modes, or WGMs.
Like sound in St. Paul's Cathedral.
Exactly that principle. It keeps the light interacting with the magnons near the surface for a very long time.
Okay, connecting this back. This strong coupling, this amplified conversation between light and magnons. What does that unlock? What's the big picture?
Well, it opens up really exciting possibilities for new quantum technologies. Think about it. Light is great for sending quantum information over long distances, but hard to store. Magnons, in materials like YIG, can potentially store quantum information for relatively long times, but they don't travel well.
Do you need a translator?
Exactly. These optomagnetic systems could act as quantum transducers, converting quantum information faithfully between photons and magnons. You could have magnon-based quantum memories, interfaces for quantum computers, highly sensitive detectors. It's really a new frontier for building quantum devices.
Wow. Okay, so let's try and wrap this up. What should you, listening, take away from this? We started with a simple compass and ended up deep in quantum mechanics.
Yeah, I think the first key thing is that magnetism isn't really classical. It's fundamentally rooted in electron spin, an intrinsic quantum property, and driven by the exchange interaction, which is this powerful effect arising from electrostatics and the Pauli principle, not simple magnetic attraction.
Right. And the second point is about magnons. These are the collective waves, the ripples in the magnetic order, the quantized excitations like phonons for sound. Understanding them is key to understanding magnetic materials.
And third, this new field of cavity optomagnetics. By using optical cavities to trap light, we can dramatically boost the normally weak interaction between light and magnetism, reaching strong coupling.
Which opens the door to all sorts of potential quantum technologies like transducers and memories by linking light and spin waves.
It really feels like we're just starting to figure out how to truly harness these deep quantum phenomena that underlie even everyday things like a compass or a computer hard drive.
Which leads to a final thought to leave you with. What other common, seemingly simple interactions all around us might be hiding equally profound quantum secrets, just waiting to be unlocked for future breakthroughs?
Something to ponder, definitely.
What an amazing journey. If you found this deep dive fascinating and you want to explore more of the quantum world or other complex topics, please do like this deep dive, subscribe to the channel, maybe check out our affiliate links if you're feeling supportive, and definitely leave us a comment suggesting what topic you'd like us to tackle next.
We love getting those suggestions.
We really do. Thanks for joining us, and we'll see you on the next deep dive.